Hi all, it's me Adithyan from Excel Education Center. So welcome back to our part 2 of rapid focus session. So we are going to continue the chapter current electricity. To the first topic, factors affecting the resistance of a conductor. Which are the factors affecting the resistance of a conductor? We all know that. The resistance is actually, just wait a second. The resistance is actually directly proportional to length of the conductor, and resistance is inversely proportional to area of the conductor. There are two terms. Resistance, it is directly proportional to length and it is inversely proportional to area. So then when we will be end up with a concept something like R directly proportional to L by A. R directly proportional to L by A. So just wait. Okay, so I can show you another form of this representation, something like R is equal to L by A. Actually, there is a minute change in these two statements. Actually, there is a very minute change in these two statements. What is the change? In the first one, it states that resistance is depending on length and area. Okay, it's depending on length and area. It can be depending on any another quantity also, but it is depending on the length and area. What is the second equation suggesting that? The resistance is depending only on length and area. Okay, there is a clearly there is a difference. Okay, what is the impact of this difference actually? Okay, so let me consider. I'm considering a plastic wire with a length of 1 meter, and area of 2 meters square. Okay, and I'm considering a copper wire with exactly the same length of 1 meter and area of 2 meters square. Length of 1 meter and area of 2 meters square. It's clearly, you can observe that the area is actually exactly the same. The area is exactly the same, the length is exactly the same. If resistance is only depending on the length and area, then the resistance of these two will be exactly the same. The resistance of these two should be exactly the same. But in reality, the resistance of these two are not the same. Why? The length is same. Yes, of course, the length is actually same. The area is same. Yet the resistance is not same. Why? Because the material has changed. First one is plastic, the next one is copper. So we have to consider the nature of the material. That's also an important factor. Okay, you consider length, it's good. You consider area, it's very good. But you have to consider you have to think about the nature of the material. So this actually the equation will be something like this. Okay, what will be the value? Resistance is equal to rho L by A. So you can clearly see there is an additional term. Rho. What is rho? There is an additional term rho. I introduced this term rho to represent the nature of the material. So rho means, rho is an indication of nature of the material, not a point, and it is a very important point. Rho is actually the clear indication of nature of the material. This is the nature of the material, which is known by the term, or it is called by the term specific resistance or resistivity. These two terms are familiar. I know these two terms are familiar, you know. So the term resistivity is more popular than specific resistance, but you have to understand these both terms. Resistivity and resistance means exactly the same thing. Nature of the material, raw nature of the material. Okay, is that okay? So there is one more thing you should know. Here R is directly proportional to L by A. We have to introduce some kind of constant. To make this proportionality as an equation. So rho is introduced as a constant. Yes, rho is introduced as a constant, and that point is very, very, very important point. Understand this. Rho is a constant. It's a very much important thing. Rho is a constant. It's very important thing that rho is a constant. Not the point. Okay, you have to highlight 2 points from this section. Which are the 2 points? First point is rho is a constant, which indicates the nature of the material. These 2 points are very important. Highlight these 2 points. Okay, you can take a screenshot of this note, or if you really want to know this question and note, you can just simply ask me directly. So I will send you the notes. Okay, personally, fine. So R is equal to rho L by A. So that's it. Okay. So how we can define? So it is not completed yet. Okay. We are end up with an equation. Yes, that's right. We are end up with the equation. Still, yeah, we have to give a proper definition. How we can find a proper definition? So R is equal to rho L by A. So I can rechange this equation into rho is equal to R by A. RA by L. Yes, that's fine. It's clearly okay. So you have to give the definition for resistivity. Just understand these things. Okay. I have clearly, absolutely, I have no clear idea about resistivity. That's the reality. I know that it's something related to nature of the material, but I have clearly, absolutely no idea how to explain it. Okay. So, but I have an idea. I have a clear idea about length. I have a clear idea about area, and I have a clear idea about resistance. So you can use these known terms in every situation, in every mathematical problem, or in every equation. You have 2 options. First one is a bunch of terms that is you are really used with, and there will be a term which you have absolutely no idea. What happens, the majority of students, the majority of kids do the same problem. They focus on the term which is not familiar. That way of approaching makes the situation more difficult. Understand this. That kind of approach will make the situation much worse. Okay, so it's already worse, you can make it more worse. So just understand this. Always look into the familiar terms. Okay, just imagine that you are going to a family function. You are going to a family function. Okay, so first thing you will be looking for your cousins, the persons you know, or the persons you like. Okay, that's the first thing. Then only you seek about others. That's exactly how we going to approach a problem is exactly the same. Okay, when we are facing with a problem in life, okay, in life also, first thing we are going to do is we are looking for our closed ones. We are looking for our friends, parents, or any kind of that kind of persons. Okay, so that's the first thing we have to do. That's the first thing. That's the immediate thing you have to do. So in any problem, if we end up with a bunch of terms in which there are terms that I know clearly, I know the concepts, and at the time I have no idea about that. So just ignore that term which that you do not know. So and just concentrate on the terms that you know. R, A, and L. I'm simply putting the value. A is equal to 1 meter square. I'm putting a value area to 1 meter square, giving a unity. Unity is very important. So that's it. A is equal to 1 and L is equal to 1 meter. Then the resultant will be rho is equal to R into 1 by 1. 1 by 1 is 1. Rho is equal to R. So we will be end up with a conclusion, an equation that which says that resistivity is actually resistance. That's it. I solved the mystery. I solved the problem. I have no idea about this term, but it is find out that the resistivity is actually the resistance. Nice. It's very easy to find. It's very easy to now understand that. What do you mean by resistivity is exactly the resistance. What is the resistance? Resistance is the opposition to the electric current. So that's it. So we know that resistivity and resistance are exactly the same term. When a body with a unit length and a unit area of cross section. Just consider this. If we have a conductor, this is a conductor with a length of 5 meter, then we call it as resistance. If I'm cutting this at a point where the length is a 1 meter, then I call the resistance of this particular piece as resistivity. Now you know the concept. How I explain the term, difficult term resistivity? By using the known terms resistance, area, and length. That's the point. Okay, so always in any kind of problem, always look into the familiar topics, familiar terms, not into the terms that you have absolutely no idea about. So that's it. Okay, so here I explained every terms and I explained everything. So we can go to the questions actually here. So we are taking too much of time. the relation connecting resistivity and relaxation time, it is also given by rho is equal to m divided by n square tau. And there is a temperature dependence of resistivity. Actually, we know that the resistance and temperature are interconnected, and also the resistivity and temperature are also interconnected. Something like rho t is equal to rho 0 into 1 plus alpha into t minus t0. Okay, alpha is a coefficient of this thing. It's a constant actually. I can explain the problem section. So these are the basic equations that you have to remember in the topic resistivity. Which are the basic equations? First equation is obviously R is equal to rho L by A, and the second equation is rho is equal to Ra by L, and the third equation is the relation between resistivity and the relaxation time. It's actually one of the most important equation, and the derivation is also important to the board exam, not to entrance exam. The derivation is actually kind of important in the board exam. Okay, so and the final equation, the temperature dependence of resistivity. Okay, here we go. So we can go to the questions, right? Okay, so okay, clear. So let me know in the comment section. So we are going to the first question. The resistivity of iron is 1 into 10 raised to ohm. Okay, good. Okay, ohm meter. So I am writing the resistivity. Okay, I'm changing the color. I think red will be not good to see. I'm using the color black. Okay, is that okay? The resistivity is actually 1 into 10 raised to minus 7 ohm meter. That's good thing actually. The unit is actually in ohm meter, so there is nothing to worry. It's actually easy to do. The resistance of an iron wire of a particular length and thickness is 1 ohm. Okay. If the length and diameter of wire both are doubled, then the resistivity will be, okay, it says that length is changed into 12 and the diameter is changed into 2e. So what will happen to the resistivity? Okay, many of the students will imagine that, many of the students will simply write the equation rho is equal to Ra by L. Then they put the value for, okay, it is the original resistivity. So the new value will be rho dash is equal to, the resistance is exactly the same, A dash by L dash. And many of them put this value L dash to 2L and do all the mathematical stuff and get into a particular value. But that kind of approach is actually not correct. The first thing you will do is exactly the same thing. That's okay. Actually, that's not a problem. It's okay, fine. So, but you have to understand the concept. You have to understand that what is meant by rho. Okay, rho stands for which thing? Rho stands for the nature of the material. Yes, that's it. Rho is the term that I introduced to indicate the nature of the material. Okay, we can go to the previous section. Here we go. I introduced the term rho as a constant to implement the nature of the material, So here, the nature of the material is iron. Here, the nature of the material is actually iron. Then the length and diameter is doubled. So what? If I take a 1 meter length of iron and I just stretched it, the iron will convert into gold or something else? No, the iron will be still iron. So the nature of the material do not change with the length, area of or any kind of that thing. Okay, so you have to understand that rho is actually a constant. It is not going to change. Unless the material is changed. That's the point. It is not going to change unless the material is changed. So if the material is not changed, so the rho will be exactly the same. So the value is 1 into 10 raised to minus 7 ohm meter. So the values is exactly the same, 1 into 10 raised to minus 7 ohm meter. That's it. So we know the answer for that particular question. It's actually very easy one. So go through the questions. Okay. Moving to the next question. Okay. According to the question, the temperature coefficient of resistance for a wire is. Okay. We have all know the term what is meant by temperature coefficient. Okay. What is temperature coefficient? The temperature coefficient is represented by alpha. The term alpha means actually in this question 0.00125. Okay, so it's a given value. Alpha is equal to 0.0125. Okay, at 300 temperature. So what is the value at 300 temperature? That's the first temperature. So T1 is 300 Kelvin. At 300 Kelvin, the resistance is 1 ohm. It's very simple. Okay, the temperature at which the resistance becomes 2 ohm. We want to make the resistance as 2 ohm. Okay, we want to make the resistance into 2 ohm. What will be the new temperature? At what temperature the resistance will become to the value of 2 ohm? So that's the question. T2 is equal to question mark. Okay, actually it's a very simple question. We have a direct equation which connects temperature, resistance, and alpha. What is the equation? Okay, we can go to the equation. The equation is something like this. Okay, so equation says that R is equal to, or the new resistance is equal to, R is equal to R0 into 1 plus alpha T. So it's a direct equation actually. In this equation, then old resistance or the first resistance is actually 1. The new resistance that we need is 2 into 1 plus alpha into delta T. The value alpha is equal to 0.00125. That's given. How will you find the change of temperature? Okay, by subtraction. T2 minus T1. Okay, the final minus the initial. Okay, here we go. So we want to find the T2. The T1 is already given by 300 Kelvin. Okay, so applying these values over here, we will be end up with the value of alpha is 0.00125 into delta T. That's enough. Okay, so opening the bracket actually, okay, you will get 2 is equal to 1 plus the value will be multiplying a digit with 1 will give you exactly the same reading. Okay, 0.00125 into delta T. So in this case, taking the term 1 over here, then it will be 0.00125 into delta T is equal to 1. Is that okay? Clear? Done. Then we have to find the temperature. So delta T, making the equation something related to temperature, delta T is equal to 1 divided by 0.00125. So the delta T will be 1 divided by 0.00125. Just you have to imagine. You can find it in a very simple manner. Okay, so just keep on this term 125. So 1, 2, 3. Okay, I am taking it as a 125. So I have to imagine the upper value will be 1000. Okay, adding 3 zeros. Okay, 3 zeros. That's it. Okay, so 1000 by 125. What is the value of 1000 by 125? If you divide 1000 with 125, you will be end up with the answer of 8. And applying these decimals, considering the decimals also, the reading will be 800. So that's it. Okay, it's a very simple mathematical step I have made. I'm sure it will be easy. Okay, fine. So the delta T is actually given by 800. Okay, so what is delta T? Delta T is actually T2 minus T1 is equal to 800. So what is T2? T2 is equal to 800 plus T1. So in this session, okay, in this question, what is the value of T1? The value of T1 is 300 Kelvin. Okay, you have to substitute this value over there. So you can get a result of T2 is equal to 800 plus 300. So the sum of 800 and 300 is 1100. So the value will be 1100 Kelvin. So there is an option B which says the temperature will be 1100 Kelvin. Is that okay? Clear? So we have done the problem which relates the temperature and temperature coefficient of resistance and new and old resistance. Okay, fine. Okay, so next section gives if NER. So we go to the next section. If NER and M respectively the density, charge density, it's actually charge density, it's actually the charge density, relaxation time and mass of the electron. Then the resistance of a wire of length L and area of cross section A will be. So you have to relate that resistivity with the relaxation time. How would you relate the resistivity with the relaxation time? Resistivity is equal to M divided by Ne square tau. Rho is equal to M divided by Ne square tau. You know the equation here. So something like the M divided by Ne square tau. So M divided by Ne square tau. So actually the value is actually exactly the given below. The first option, look at the first option. It is actually M divided by Ne square tau. And there is actually a length and area is additional terms. So you don't have to worry about that. The answer will be M divided by Ne square tau. So we are stepping into the last part of this video. So relation connecting EMF and internal resistance. It's also actually an important topic to do with the So we can go to the topic, relation connecting EMF and internal resistance. Okay, so to every body there is an internal resistance. Understand this thing. To in every cell there will be an internal resistance. If you are going to buy a cell from just a shop, you can find a value something. You are going to buy a battery. Okay, fine. A cell is mean by battery. You can see that the voltage will be something like 12 volt. The theoretical voltage will be 12 volt. When I am connecting this battery to a actual circuit, we are ending with a value. We are ending with a value 10 volt. 10 volt. Actually, there is a decrease in 2 volt. This decrease in 2 volt is due to the internal resistance. It is due to the internal resistance. So, relation connecting internal resistance. Okay, here we go. The circuit has a resistance of capital R. The internal component has a resistance of smaller r. So, the effective resistance is capital R plus smaller r. Because these two are in a series combination. Thus the current is I is equal to epsilon by R plus R. So we can simply just consider this. Okay, I can expand this. It's actually very easy. So just to go, we are just applying the Ohm's law actually here. According to Ohm's law, we know that volt is equal to current into resistance. Here the resistance is capital R plus smaller r. So I is equal to IR. So E is equal to IR plus IR. What is IR? Actually, IR is the actual real volt we are getting. So E plus V into IR. So that's it. Okay. So we can write V is equal to E minus IR. It is a one identity. Or we can go for the internal resistance. What is the value for internal resistance? Internal resistance will be E minus V by I is equal to R, internal resistance. So these are the equations you have to remember in the term relation connecting EMF and internal resistance. And it's quite pretty much important topic. So just remember these equations, okay? So we are going to end up with the last and final section, okay? So the Wheatstone bridge, okay? So we are going to the exact concept of a Wheatstone bridge. Okay, you know the Kirchhoff's first rule, second rule, applying all the equations, and you doing very kind of mathematical stuff. Just neglect all of it. We are going through the concept. Okay, what do you mean by what is the purest concept of Wheatstone bridge? Okay, so here we go. In a Wheatstone, actually, okay, there is a resistor connected. Okay, and there is another resistor connected. And here we go, another resistor connected, and it is another resistor connected. Okay, and we know that we apply a condition in which Ig is equal to 0. It is known as balancing condition. What is Ig? What is meant by Ig? Okay, here we go. There is a galvanometer. Here we go. There is a galvanometer is present. So when we are connecting these two with, okay, we want to make sure that Ig becomes 0. Ig becomes 0, which means there should not be a current flow from. There should not be. Okay, I am placing this point as A and B. A and B. So the meaning is actually the Ig is equal to 0, which means it's a galvanometer, and the galvanometer current should be 0. When when will be the current flow? Current flow from higher repulsion to lower repulsion. If there is no current, it means that repulsion at A and repulsion at B are exactly the same. The potential on A and potential B are exactly the same. It is the only case in which current flow will be 0. So that's it. So we have to make sure that the potential of A and the potential of B should be exactly the same. So here the potential and here the potential should be same. So this potential and this potential will be same. So we are end up with a mathematical expression. So we are applying this exactly the same value over here. So this is the point. So this potential and this potential should be exactly the same. These two potentials should be exactly the same. So I'm writing this value as something like, so I'm writing this, the 10, okay, the upper volt and the lower volt, the 10 and 30 should be exactly the same. Applying the same concept on the right side, on the other half, on the other arm, you will end up with something like this. These two potentials will be exactly the same. These two potentials should be exactly the same. Okay, which potential should be exactly the same? R and 9 should be exactly the same. So when we are applying the same value, R and 9 should be exactly the same. Okay, so here we go. I am placing R should be equal to 9. So R should be equal to 9. So dividing these two, we will be end with a, so actually it's not R, it's actually R1. 10 by R1 is equal to 30 by 9. Okay, so 30 by 9, sorry, it's actually 30 by 9. By rearranging it, we will be end up with 90 is equal to 30 R1. R1 is equal to 90 by 30. So it will be 3 ohm. It will be 3 ohm. So R1 should be 3 ohm. It's clear that R1 should be 3 ohm. In the option, R1 should be 3 ohm. In the option, there is R1 should be 3 ohm. And you can see that there is another Wheatstone is present within the Wheatstone. Okay, you can clearly see that there is another Wheatstone is present within the Wheatstone. But there is nothing to worry about that. If the first Wheatstone is in balanced condition, just imagine if this first one is balanced condition, which means if there is no current is flowing from B to D, if there is no current is flowing from B to D, then there will be no current will be flowing from the internal Wheatstone bridge, okay, the small Wheatstone bridge. So it's actually there to confuse us. It has no significance. The R2 value, the second reading can be any value, any finite value. That's okay. Okay. So R1 should be 3 ohm and R2 can be any value. It doesn't depend. It doesn't matter what is the value. Okay. So that's it. Okay. So we are discussed the chapter current electricity in a pretty good way. So I think you all enjoyed the session. So we can see in the later video with a good chapter. So just let me know in the comment section. Okay.